Hi, I'm Jaya Jose from Johns Hopkins University, and I'll be presenting our paper Overcomplete Deep Subspace Clustering Networks in this presentation. First, let us start with a brief introduction about subspace clustering. Subspace clustering involves grouping a set of similar data points in an unsupervised way. If X is a matrix of dimension D cross N, such that the columns in it are chosen from a union of K subspaces of dimension D, the task of subspace clustering is to categorize the columns of X into their corresponding subspaces. There have been many methods explored for subspace clustering over the past 10 years. Of these, self-expressiveness property-based methods are widely used as they are more robust to corruption by noise. The self-expressiveness property can be represented as X is equal to XC, where C is the self-representation matrix. Using that idea, the problem can be represented as an optimization problem as this. Notably, deep subspace clustering is one of the recent methods that uses a deep network-based solution for subspace clustering, which improve the performance by a huge margin compared to the previous methods. In DSC, a self-expressiveness layer is introduced in the latent space of an encoder such that the latent representations are suited for subspace clustering. However, there are two main issues with DSC. First, it is not that robust to noise. From our experiments, we found that the change in performance with the addition of noise is highly notable. Also, in DSC, the autoencoder is first trained for reconstruction and then fine-tuned for clustering. We found that in DSC, the place we stop the pre-training matters a lot. This is done by looking at when the reconstructions look visually good in DSC. However, this is not a good approach, and the change in performance is very drastic when we stop the pre-training just some epochs before or after the nominal epoch. Hence, we propose using overcomplete networks which are more robust compared to normal undercomplete networks used in DSC. We note that overcomplete representations in signal processing uses overcomplete bases so that the number of basis functions is more than the number of input signal samples. This enables a higher flexibility for capturing structure in data and thus allows it to be more robust. So similarly, for convolutional neural networks, we take the input image to a higher dimension spatially by using upsampling layers after convolutional layers. We can notice that this causes the receptive field to get constrained and thus focus on more fine features when compared to normal undercomplete networks. The feature maps extracted also show us the difference in the features that are extracted. In our proposed method, in the autoencoder, we propose using two branches, one undercomplete branch and another overcomplete branch to capture both representations. Then we fuse them before passing them through a self-expressive layer. The decoder used here is an undercomplete decoder. We first pre-train the network for reconstruction and then fine-tune it for clustering along with the self-expressive layer. Then we take the weights of the self-expressive layer to form the self-expression representation matrix C. Spectral clustering is then done on this to get the clusters. To train this network, we first use a normal reconstruction loss while pre-training the network for reconstruction. Then we fine-tune it using the self-expressive loss. We conduct experiments across 4 different datasets where we note that our proposed method, ODSC, performs better than the previous methods. We conduct an ablation study in which we start with just the undercomplete autoencoder network, and then you experiment on the overcomplete autoencoder network. So in these experiments, we found that the overcomplete autoencoder network, when trained for subspace clustering, actually performs better than the undercomplete. And then when we fuse both the representations, we get the best results. We also note that our method is not as dependent on pre-training as DSC. We also see that the reconstructions of overcomplete network is far better than undercomplete network, which shows that the overcomplete network actually learns better representation to reconstruct the image. Also, we conduct an experiment in which we add noise to the input data and see how it affects the robustness of the proposed algorithms. We see that our method performs better even under noise. The code is available